Sorry.
Okay, so on the assignment that I just gave back was probably summation of probably the most annoyed I've ever been reading any of your assignments in this class. Okay? Couple of things, like it was problem number 2 where you were given a mass and like I don't even remember what the numbers, but it had 3 significant digits in it. And then when you convert it into moles, a lot of you just put 0.24 or whatever. When you're converting from grams into moles and you have like 3 or 4 digits in the mass, that's how many digits you need to keep in that mole conversion. Don't round it. Also, and again, you have to view this assignment from how you do it from my perspective when I go to grade it, when I'm cranky. Call one word. Okay? Like, for example, you have different parts of, like, say, for example, number 2. Okay? I want the work that goes with it right here. I don't want arrows. I don't want it to turn into a matrix where you have, like, 4 different problems worked out over there, and then I have to guess which one it is. I'm not. Okay? You keep that work right beside that answer. It's not a difficult concept. If I were your boss, literally a third of you, I would just walk in and you would show up today and I would just fire you. Okay?
Would I get a bonus?
Not after the ray diagrams that you drew.
Whoa,
you
2 separate classes.
Well, I'm just telling you, you get canned on your ray diagrams.
Make a shot.
So don't get cocky.
Oh dear.
So, be successful in the little things. When someone, your boss, me, whoever says, this is how I want it done, guess what? If you're not successful in the little things, they're not going to trust you with the big things. Okay? Someone says, look, this is how I want it done. Guess what? Do it that way. Because there's the method to my madness, because I've got to grade like 19 of these papers. I don't want to waste my time sorting through random numbers that don't mean anything. Okay? I care for you all deeply. I'm not going to do it. Okay? So keep the work beside the answer and no arrows.
Okay.
All right, no.
In my defense, I was doing the assignment that was due that day when you were explaining not to use arrows.
So you realize that does nothing to support your argument.
So it's not if I knew you said don't.
When I gave out the assignment, I said don't do that.
He said it before in previous assignments.
It is like I didn't teach you physics.
That was like 2 years ago.
Okay, seriously? Your attention span is that short? No arrows. The only arrows that are going to show up are the ones that I draw on your arrow going through your apple. Okay. Now, let's talk about bringing down my blood pressure, shall we? All right, so on the lab. So if somebody had asked about which ones, Isaac, what did you want to talk about?
20.
Okay. Oh, but you got to jump back up. Okay, so here's the story. So, by the way, quiz tomorrow, 3rd quiz. Okay, if you really want to plan ahead, you get your 3rd quiz tomorrow. That's going to be like where you have to do it in stages. We're like, hey, what's the initial concentration? Here's what's the pH after you add no base, after you add 10 milliliters of base, after you add 20 milliliters of base. Okay. You're going to have both non-buffered and buffered solutions in there. Okay. You're not going to have to write out the names and formulas of any of the strong acids. What I am going to do is I'm going to give you a list and say, is it a strong acid, strong base, weak acid, weak base? Okay? That's what you're going to have to be able to recognize, right? So that's the deal. So it's also going to be 1 page front to back, but a lot of that is big open spaces where we can work out the problem. All right. So here's the point, and this goes back to when you have this sodium acetate and you're comparing the 3 graphs. So here's the bigger idea, and this boils down to question number 8, okay, as well. So if you look at your answers for 5, 6, and 7, okay, So those should range from about 5 to about 6.5. Okay? Ish. Somewhere between 5 and 6.5. But again, go beyond just the calculations. Okay? Look at what that trend is. So when you're looking at this, there's a couple of things that are important. First off, understand the importance of this Ka value. And this is going to be important today when you get into KSP values, because it's the same mathematical concept. So it's always your products, in this case your hydrogens and your anions, over the concentration of the acid. Okay? It's always products over reactants. So remember that today when we get into KSP. It's always products over reactants. And mathematically, Mother Nature wants to reach that Ka value. And it's almost impossible for me to overstate the importance of this. Mother Nature, at all costs, wants to be in equilibrium. So even if you go back to number 1, okay, if you look at this reaction, it's HA, you're getting hydronium ions and your anion. Cool, okay? You're not titrating it. There's no hydroxide, nothing. Here's your rice chart. Boom. So if there's nothing added, like this is 0.1 molar, 0, 0. Old school. Plus X, plus X. Okay? 0.1 X, X. Old school. This should not give you any trouble at all. You should be able to do this calculation without any hesitation at all. So the answer to number 1 should be around 3. Okay? Ish, something around 3. Now, then you want to calculate that pH after you've added a certain amount of base to it. Okay? But here's the bigger truth. When you look at what's going to happen here, and you have that hydroxide reacting with the water, and you're making water and the anion. Okay? So if it's a buffered solution, your anion concentration isn't starting at 0. But Mother Nature still wants to reach the same equilibrium. Okay? This is the most vital part of this story, is that Mother Nature is going to achieve equilibrium no matter what she has to do. So if you look at what's happening in this question on number 8, explain the trend in your answer number 5 and 7. Now, I tell you what you want to mention. I said, explain in terms of the amount of hydronium ions required to establish equilibrium, Ka, anion concentration, and the resulting pH. So make sure in your answer to number 8, you have mentioned all 4 of those things. Okay? Easiest thing to do is start with the Ka value. On 5, 6, and 7, does Mother Nature still want the same Ka value?
Oh, yeah.
Yes, absolutely. Mother Nature still wants the same Ka value. So if you look at this in terms of how that's calculated, your hydronium ion times your anion concentration divided by the concentration of the acid. Okay? Same Ka value. As your anion concentration increases, what happens to your Ka value? Absolutely nothing, because that's the sweet spot. That's that Ka value. But as your anion concentration goes up to produce the same Ka value, what happens to your hydronium ion concentration? It goes down. Okay? Because of the fact that you need fewer hydronium ions to produce the same Ka value. Okay? That's one of the most important things that you have to understand. Now, that's also why when you look at that pH versus volume graph, okay, here, okay, you should have kind of 3 distinct lines. The non-buffered solution, the first buffered solution, and that second buffered solution. Okay, it probably looks like a plate full of spaghetti, but that's just roughly what it should look like. And on that first one, and only on the first one, because that's the only one that's a non-buffered solution, that's what you're going to go through. You're going to draw a line at the equivalence point. You're going to go to half the equivalence point, and then you're going to draw a line over here on that pH to find that Ka value. So your graph, this is what your graph should look like. You have all 3 all three pH curves on the same graph. Make sure I know which one is which. Do not draw 3 lines on there and go, oh, Burkamp will know which one it is. No, Burkamp won't know which one it is. Okay? Color code them. Do dashes, lines, something, label them. Okay? Make sure that I can clearly see which ones are which. Okay? Now, I don't know what happened to our deionized water system, but here's what I want you to see out of questions 11 and 12. So, it's just funny, most of the time, coming out of that DI system, it's usually acidic for whatever reason. Something changed and it became horribly basic. I don't know why, but here's the bigger idea. So what you should see, hopefully, is that when you did number 11, is that you should see a drop in your pH. Okay? Now, the problem is we started horribly basic, so that one actually should show up. But again, listen to me. And you have to understand the difference between something being an acidic versus pH. They're related, but they're not the same thing. So if you look at how that pH probe works, the mechanics of that pH probe, basically what it does is that it measures the potential difference across 2 electrodes, and then it runs it through an algorithm that says, hey, based upon this potential difference, this matches up to a certain concentration of hydronium ion. Now, listen to me. This is the concentration of hydronium ions, not necessarily the concentration of the acid. So you could have acetic acid, H3O2, versus hydrochloric acid, which is HCl. They both contain hydronium ion. Don't get me wrong. They both contain hydronium ion. But what's happening is that this has them, but they're not free ions floating around in the solution. They're bound up with the anions. Versus if you have hydronium ions and from the hydrochloric acid, those are floating around. So they're both acids. Okay? So one of the things that I figured out is that you can't confuse something being an acidic solution versus the pH. They're related, but they're not the same thing. Because if you look at the mechanics of how you determine pH, it's the concentration of the hydronium ion. So what happened is that when you added that ammonium chloride, NH4, don't worry about the chloride, it's not part of the story, okay? It's just a spectator ion. So the only way that you can make that pH go down is one and one way only, is to increase the concentration of the hydronium ion. That's it. So basically what happens is that this is ammonia. We'll spend a lot more time talking about ammonia when we get into structure. And it has this unbound pair of electrons. So it has this dome of negativity up there. And it has this hydronium ion basically attached to it. So here's this molecule, and it has a St. Bernard lurking around the negative end of it. Because this has this excess pair of Chihuahua, so there was a St. Bernard hanging around. Okay? So basically what happens in the water, it also has its own dome of negativity. It actually has 2 pairs of Chihuahuas around the outside of it. So basically what happens is that this St. Bernard leaps from here and goes over to the water. Now, at this point, the pH probe can recognize that, because the pH probe can recognize hydronium ions. It can't recognize ammonium ions. We don't have PNH4 probes, okay? We don't have them. We have pH probes. So the only thing that can measure is the concentration of the hydronium ion. So this St. Bernard jumps ship, goes over to the water. Now the pH probe goes, oh, this is something I can recognize, because it's calibrated to recognize the presence of hydronium ion. And the pH goes, oh, we have a higher concentration of this. We're going to change the display on the LabQuest, and I want to make that go down. Okay? We don't measure the ammonium or the ammonia we can only measure what's happening with the hydronium ion. So you see that drop. Cool, right? Great. You see that pH go down. Did y'all see it go down? Oh, fantastic. I love it when chemistry works. Sometimes it doesn't. That's always tough to explain. What happened? I don't know. Just go with this. So you saw that pH go down. But again, the only way that happens is to increase the presence of the hydronium ion. So then the challenge becomes, what happened? How did you generate excess hydronium ion? It's because that St. Bernard jumped ship and went to the Chihuahuas on the water as opposed to the Chihuahuas on the ammonia. Okay? Cool with that. Now, in contrast to that, you did the sodium acetate. The sodium acetate, you have the C2H3O2 and water. So at this point, this is short a St. Bernard. Okay, it's missing one. And if this is a chloride ion, you put it in the water, absolutely nothing would happen, because chloride ion is a horrible base because it came off of a strong acid. This is why if you titrate like a strong acid, hydrochloric acid, bromic acid, whatever it is, when you hit neutrality, pH is just 7. The anions are there, or they could care less about the water because they don't want to reform it. But you put this in here, it reacts with the water. You make acetate ions, and more importantly, you generate hydroxide ions. Now again, listen to me. We do not have POH probes. We have pH probes. You're going, great, you have hydroxide ions. You're generating those. But again, you know that the hydronium ion concentration times your hydroxide ion concentration always equals the autoionization constant of water. Okay? So when this happens, you boost the hydroxide ion concentration. You're not making hydronium ions, okay, but you're boosting the hydroxide ion concentration. When you boost the hydroxide ion concentration to make everything balance out, what does Mother Nature do with the hydronium ion concentration? It goes down. Okay? So we're not making more hydronium ions or adding, we're increasing the hydroxide ion. Mother Nature goes, oh, this is bad. I sense a disturbance in the force. So Mother Nature goes, hey, I want to keep the same, notice the recurring theme of KW, which means that it's in equilibrium. So Mother Nature goes, hey, you want to boost the hydroxide ion concentration? Fine, I can handle this situation. Mother Nature goes, I'm going to decrease the concentration of the hydronium ion. So what you see showing up on that pH probe, because that pH probe is sensing a smaller voltage difference in terms of the hydronium ions, and Mother Nature goes, hey, there's a smaller value. I'm going to make that pH then go up. So it isn't sensing the hydroxide ions, it's just sensing a change in the hydronium ion concentration. Okay? So get out of your minds, oh, pH probes measure pOH. No, they don't. pH probe is a one-trick pony. It's a very good trick, okay? But it's a one-trick pony. It only measures the concentration of the hydronium ion. Okay? Got it? Good. Green. All right. Did I answer your question, Isaac Reese? Yeah. You're feeling good about it? Okay. Anybody else have any questions on the lab? Okay, so here's what I want. I want the, how do I want this? I know, what was the first page? What color was the first page? I did it wrong.
Yeah, they were all white.
Okay.
Except for the
So yeah, so I want this, page 1. Data, page 2. Blue sheet, graph. So front page, data, blue sheet, graphs. There we go. Mark, you stop that.